Today I will be presenting our paper titled Far-Field Minimum Fuel Spacecraft Rendezvous using Coupon Operator and L2 by L1 Optimization. The overview of the presentation is as follows. First, we briefly introduce the problem of spacecraft rendezvous, followed by the literature review on the same. Then we motivate the problem by discussing the main limitations of the earlier works and then discuss the main contributions of this work. This would be followed by providing a brief overview of spacecraft rendezvous and the coupon operator. Next, we discuss the problem statement, followed by our approach to solve the problem. Finally, we discuss the results and make some concluding remarks. A rendezvous mission is usually divided into far-field rendezvous, near-field rendezvous, and final approach. The near-field rendezvous and final approach rendezvous is when the distance between the active and target spacecraft is much less than that of the distance between target spacecraft and the planet. For these types of rendezvous operations, various control approaches have been proposed. For instance, robust H-infinity, adaptive control, neural network based and artificial potential based methods. The control design in such problem is based however on linearized equations of motion such as HCW equations, which correspond to a time invariant system of equations, or the TH equations, which correspond to a periodic linear system. These widely used linearized models are rarely effective to describe the relative motion for far-field rendezvous, where the distance between the active and target spacecraft is of equivalent or larger magnitude than the distance between the target spacecraft and the planet. In this slide, we discuss the limitation of earlier works and then the main contributions of this paper. The limitations are as follows. First, the use of linearized spacecraft rendezvous equations may not give sufficiently accurate results for far-field rendezvous. Next, the use of nonlinear rendezvous models may possess the known challenges of nonlinear control and may also be computationally heavy. Now we discuss the main contributions of our paper, which helps us to address these limitations. First, we use a coupon operator based approach to convert the nonlinear model into a lifted space linear dynamics. The key idea of the coupon operator is that the nonlinear dynamics of the rendezvous problem can be approximated by a higher dimensional linear state space model based on which we can compute approximate solutions to the minimum fuel rendezvous problem. The coupon operator approach utilized herein allows one to account for the nonlinearities of the dynamics of the rendezvous problem, while at the same time linear control design techniques are still applicable. Next, we propose a modified version of the iteratively recursive least squares approach to solve the minimum fuel problem for the thrust vectoring spacecraft. In this and the next few slides, we briefly review the classic problem of rendezvous and the coupon operator. Consider target spacecraft moving in an elliptical orbit around a planet as shown in this figure. The problem is for the active spacecraft to perform a rendezvous operation with the target spacecraft. We use a LVLH frame for the representation of the rendezvous dynamics, where the origin is at the target spacecraft, the z-axis is from the target spacecraft to the center of planet, the x-axis is perpendicular to the z-axis and is on the elliptical plane, and the y-axis follows the right-hand rule. The nonlinear dynamics is given by equation 1. The equation is clearly nonlinear due to the terms which are appearing in the denominator. We first convert this continuous time model to a discrete time model using the Runge-Kutta method, and this is given in equation 2. In this and the next slide, we briefly present an overview of the coupon operator. Consider a nonlinear discrete dynamical system given by equation 3. The coupon operator K is a linear infinite dimensional operator which operates on a collection of observable functions Gi. Each observable Gi are functions of state and map from the state space Rn to R. The evolution of G is linear, and this is described by equation 4. However, the most challenging task is the choice of these observable functions. In general, the coupon operator is infinite dimensional. However, in practical applications, a finite dimensional approximation of the coupon operator can provide sufficiently accurate description of the evolution of nonlinear dynamical systems. Therefore, a finite dimensional observable function G is considered with dimension nk as shown in equation 5, where nk is much greater than n. In this slide, the problem statement is presented. Given the discrete time nonlinear dynamics, the initial state x0 and the final state xf, the task is to find the optimal control input u star, which will steer the active spacecraft from x0 to xf at terminal state k is equal to n, while minimizing the performance index given by equation 6. This performance index is also known as the L2 by L1 norm. Now the task is to convert the nonlinear model to a lifted space linear dynamics as given by equation 7. A data-driven approach is used to approximate the lifted space matrices A Koopman and B Koopman as follows. A set of random control inputs and a set of initial state x0 are used. These randomly generated control inputs are then applied sequentially to the nonlinear model with initial state x0 to get subsequent states. Let the control input uk be applied to take the state of the active spacecraft from xk to x of k plus 1. In this way, we construct the matrices xlift, ylift and u. Now given these matrices, the task is to minimize the Frobenius norm as shown by equation 8. The analytical solution to 8 is given by A Koopman, B Koopman is equal to xlift into Moore pseudo inverse of ylift, u. The following set of observable functions are considered. The first 6 observables are the position and the velocity itself. The next 13 observables are chosen by observing the terms in the nonlinear model carefully. Finally, the rest of the observable functions are the inverse multi-quadratic terms. The following procedure was used to generate the data for approximating the matrices A Koopman and B Koopman. To generate the sequence of data xk, we sample 1000 initial conditions which are taken from the initial uniform distribution over -1, 1 raised to 6. For each sample, we apply control inputs u of k which are taken randomly from a uniform distribution over -1, 1 raised to 3. Then for each sample of randomly generated initial conditions, we use the discrete nonlinear dynamics to propagate the states with the given control inputs u of k. For each initial condition, we simulate 2000 states along each trajectory. The terminal state can be written in the compact form as given in equation 9, where the matrices Cn Koopman, U Koopman and beta Koopman is given by equations 10a and 10b. The iterative approach presented here computes an approximate solution to the minimum L2 by L1 norm in closed form via the solution of corresponding sequence of convex quadratic programs. In particular, at every iteration j, U Koopman at time j plus 1 corresponds to the solution of the convex quadratic program given by equation 11. Here, W are the input parameters, M is the size of the control input, which is 3 in our case. Now we present the Irls Ls algorithm that is used to generate control inputs, which minimizes the performance index. First, W of 0 and epsilon of 0 is initialized to 1. Now we construct a matrix capital W and curvy W as shown in lines 5 and 7 respectively. Then the control inputs U of Koopman at iteration j plus 1, which is the solution to the QP in the previous slide, can be written in closed form as given in line 8. Then the value of epsilon is updated as shown in line 9. Next, the input parameter W is updated taking into account the computed U Koopman. This iteration is repeated until the value of epsilon at the jth iteration lies between 0 to epsilon bar, which is given. In this slide and the next slide, we discuss the results. First, we consider a near-field rendezvous in which the distance between target spacecraft and active spacecraft is much less than the distance between the planet and the target spacecraft. That is, small r is much less than capital R. Second, we consider the case for far-field rendezvous in which capital R is approximately equal to small r. Now, the control inputs are computed by using the linearized and the lifted space linear dynamics. It can be observed from this figure that these control inputs, when applied to the nonlinear discrete rendezvous dynamics, can steer the active spacecraft to the desired final state in both cases. This is mainly because for the near field rendezvous, the linearized equations can represent the nonlinear dynamics relatively well. Now consider the case of far-field rendezvous. In this also, the control inputs are computed by using the linearized and the lifted space linear dynamics. It is observed that the control input generated using the linearized equation is not able to steer the active spacecraft to the desired final states, as shown in this figure. However, control input generated using the lifted space dynamics is able to steer the active spacecraft to the desired final state. However, further, it was observed that the L2 norm of the terminal state error is orders of magnitude higher for near field rendezvous than in the case of far field rendezvous. An iterative scheme for the computation of approximate solutions to the minimum fuel far field spacecraft rendezvous problem for a thrust vectoring spacecraft is presented. Next, our approach uses tool from coupon operator theory to associate the nonlinear dynamics of the rendezvous problem with a linear system of higher dimension, which evolves in the so-called lifted state space. Finally, our numerical simulations show that the control input computed based on the lifted space dynamics can steer the system to a goal terminal state for both near field and far field rendezvous with accuracy which is orders of magnitude higher than the linearization based methods. Thank you all for your time and patience.